next presentation by Shagun and Aggarwal, who's going to be talking about electrodynamic tethers for CUAVA 2 and other satellites. So, Shagun.
Hello everyone. So I'll be talking about the use of electrodynamic tethers for deorbiting in CUAVA 2. So I'm a PhD student in the ACSER group at UNSW under Dr. Andrew Dempster and Jason Health from Civil Astronautics. And I just recently started helping out with the electrodynamic tether deployment for CUAVA 2. So in a very simple words, the very first thing that we need to understand what are electrodynamic tethers that we covered in the Cubesat presentation yesterday, but I'll just give you like a quick overview and why we are using it. So electrodynamic tethers are conducting wires which were initially conceived to connect two payloads together. But what we realized was that when we put a conducting wire with a certain velocity in the Earth's magnetic field, there's a current that was induced as a result of the two different potential difference at the two conducting ends. And with the movement of these conducting wires, a force is generated, which we can use it for our own advantage. Now, this force is driven by the space environment, which includes the magnetic field, the plasma parameters, that is the density, the temperature, as well as the solar radiations, which we could use it for a fuel-less propulsion system or a deorbiting system that we'll be doing here in CUAVA 2. Now, the very first thing that we need to understand is that what are the project goals for using the electrodynamic tether here. One is that we need to see that first it should be successfully deployed. In the previous missions that have been conducted in the past couple of years, what we've seen is that the deployment of the tether itself is a very complex procedure, and a lot of times the tether missions have failed because the tether could not be deployed, or the tether got tangled in the deployment system, or the tether snapped because it's a very thin wire. The second thing is that we are also aiming to measure the current voltage profiles that are induced along the length of the tether. The reason that we want to measure the current and the voltage is because since the current that is induced along the length of the tether varies with the plasma parameters as well as external environments like the solar radiations, and we want to understand that how the current varies, which will result in the force that is induced on the tether itself. Now, this is the CUAVA 2 design, and we are going to place the tether in the right bottom where it will be deployed using a spool. So the length of the tether that will be deployed will be somewhere between 30 to 50 meters. The length we cannot deploy a length greater than 100 meters, and because there are procedures along with limited permissions, but for a CubeSat this size, we do not need a very long tether to generate a very high force. We are using the Civil Astronautics dragon tether, which uses a yo-yo design for the deployment for the tether to roll out, and we have a weight at the end of the tether so that it stabilizes and does not recoils back or gets tangled with the CubeSat itself. The force that will be generated on the tether itself is a function of the length, the current that is induced, and the magnetic field. So it depends on the radius of the tether that we use, the angle of inclination, the velocity of the spacecraft, as well as the length that we'll deploy the tether with. Now, this is a CAD image of how the tether system should look like. Now, we're still figuring out that how we are going to deploy the tether itself, because this is the kind of the yo-yo structure where the tether will be wound upon, and on the deployment, this weight has to this tether has to come down so that it does not it is deployed with a certain speed, not too fast, not too slow. Reason being, one, it can get stuck in the system itself. One, if we release it too quick, in that case the tether might bounce back because it's a free-flowing wire, and it might get tangled up in itself, or maybe wrapped around the CubeSat because of the motion of the CubeSat body. So these are the couple of things that we're still figuring out that how we are going to deploy it, because the mission success depends on how efficiently we can deploy the tether and how long we can keep it stable. Now the tether data that we want to measure, as I told before, is the current voltage profile. So we'll be measuring it using a plasma circuit that will be separately for the tether system, where we'll use an ammeter and a voltmeter. The current and the voltage will be in ranges from milliamperes and microamperes. What we're looking at is microamperes of values for the current as well as for the voltage that will be induced along the length of the tether. Now the current that is going to be measured is a function of, as I said, the length, the radius of the tether, the plasma density, that is the M here, as well as the temperature of the charged particles. The TE and NE here, we are considering the electron current here, where we are taking the mass of the electron and the temperature of the electron also. The VF and the VB is the floating potential that is reached along the length of the tether, where the bias at the two ends change, and VB is the bias voltage that will be applied at the one end of the tether so that there's an efficient conduction of electrons. So that's it, guys. So we are actually working on the deployment system currently, and we'll start actually creating the circuit for the tether in the coming few weeks.